Learn like a pro.
All right, let's dive into a secret of the physical world. How a simple liquid, something you see every day, can be engineered to lift something as heavy as a car with what feels like almost no effort. I know it sounds impossible, but the journey to understanding it all starts with the behavior of tiny invisible particles. Have you ever been at a mechanic shop? You see a huge, heavy car get lifted way up into the air by what looks like just a simple metal stand. It honestly seems like magic. So how can a small amount of effort produce such an incredible, immense force? That's the exact question we're going to answer today. The secret to lifting that car isn't hidden in some complex engine or anything like that. Nope, it all begins with the simple, physical weight of the liquid that's inside the lift. To understand how we can create these giant forces, we first have to get a handle on the invisible pressure that exists in every single drop of water. So on the surface, a liquid has weight, right? That's just gravity pulling it down. Pretty straightforward. But the real magic, well, it happens at the microscopic level. You see, the particles of a liquid are packed so tightly together that they're basically incompressible. And this means any force you apply to them isn't absorbed. It gets immediately redirected, pushing outwards in every single direction. That right there, that is the key to everything that's about to follow. Okay, so we know there's this outward pushing force, this pressure. But how do we measure it? How can we actually predict what it's going to do? Well, luckily for us, physicists gave us a beautifully simple formula to calculate this pressure at any point within a fluid. And here it is. Pressure equals depth times density times gravity. Let's just break that down really quick. P is the pressure we're trying to find. H is the depth, basically how far down you are in the liquid. The next symbol, that's rho, and it stands for the liquid's density. Just think of it as how heavy the liquid is for its size. You know, like how honey is way denser than water. And G is just the constant pull of gravity. And that's it. Those three things, depth, density, and gravity, are all you need. And this picture brilliantly illustrates the most important takeaway from that equation. Just look at this. The pressure is the exact same at the same depth in all three containers, even though their shapes are totally different. It does not matter if you have a giant tank or a skinny little tube. If you're at the same depth, in the same liquid, the pressure is absolutely identical. And we can actually see this proven visually. It's not just a theory. If you poke two holes at the exact same depth in a tank of water, the water shoots out from both with the exact same speed, and it lands at the exact same distance. It's a perfect, simple demonstration that the pressure pushing that water out is equal at that level. So we get how pressure works in an open container. But what happens when you trap the liquid? This is where the 17th century physicist Blaise Pascal has a breakthrough that would change engineering forever. Here is the law itself. Now, the most important word in that whole sentence is undiminished. That means the pressure doesn't get weaker as it travels. A push in one spot is felt with the exact same strength everywhere else inside that sealed container, and it happens instantly. Think of the liquid as a perfect messenger for force. Because it can't be compressed, it literally has no choice but to pass that message along, perfectly intact, to every single surface it touches. This simple idea is what unlocks the magic of hydraulics. Okay, we have all the pieces now. We have our incompressible fluid, and we have Pascal's law. So let's assemble them and build the very machine that can lift a car, the hydraulic press. At its core, a hydraulic press is incredibly simple. On one side, you've got an input piston with a small surface area. You apply a small force to it, and that creates pressure in the enclosed liquid. That liquid then transmits the exact same pressure to a second, much larger piston on the other side, and that becomes our output. Now, this is the crucial math behind it all. Pascal's law tells us the pressure is the same on both sides, remember? So the force on that first piston, divided by its small area, has to equal the force on the second piston, divided by its large area. For that equation to stay balanced, if the area on one side gets bigger, well, the force on that side must get bigger too. It's the only way the math works. Let's walk through this example to really see it in action. Let's say we apply a small force, just 25 newtons, to an input piston with an area of 1 square meter. That creates 25 pascals of pressure. A pascal is just the standard unit we use for pressure. That pressure travels undiminished to the output piston, which has an area 5 times larger. So to keep that same 25 pascals of pressure, the output force has to be 5 times larger, a whopping 125 newtons. And there it is. The puzzle is solved. Just by engineering the surface areas of the pistons, we have multiplied our input force. We've taken a small, totally manageable push and transformed it into a powerful lift that's capable of raising a car. It's all thanks to the predictable properties of an enclosed liquid. But this nearly perfect system does have an Achilles heel. There is one thing that can get into the liquid and make this entire powerful mechanism fail completely. The enemy is gas. Air bubbles, to be specific. Remember, this whole system works because the liquid is incompressible. It transmits 100% of the force, no questions asked. Gas, on the other hand, is highly compressible. Its particles are really far apart so they can be squished closer together with almost no effort. So if air gets into the hydraulic fluid, your input force is no longer transmitted to the output. Instead, it gets wasted just squishing those air bubbles. Your push goes into compressing the gas instead of lifting the heavy load. The powerful multiplier effect just vanishes, and the system becomes spongy, weak, and totally inefficient. So, we've seen how simple physics, just the weight of a liquid and its inability to be compressed, can be engineered to create these incredible force multipliers. From car lifts to the brakes in your own car, this principle is literally all around us, turning small efforts into really powerful results. So the final question is, now that you know how to turn a tiny push into a massive force, what would you build with it?